Hello everyone, welcome back to another video in Math 215. Today we're going to be looking at the many theorems on limits. We're going to see the treatments of these theorems in the case of complex valued functions and complex numbers, as we've seen before in real numbers and real valued functions in Math 110. So here we see, let's say it, theorem state theorem 1. I'm going to state these theorems without giving any formal proof. Here you have f of z, where f of z is basically x plus iy, which is equals to u, which is a function of x comma y, as we've seen before, and I v, also a function of x comma y. Here, if we were to take a limit to z naught, our individual real numbers would be the following. Also, x naught plus I y naught. As in, when you take a limit, limit of a function which tends to z naught, both these real numbers, which are x naught and y naught, x and y would also tend towards the extreme, which is x naught and y naught. Now, why I said real numbers, I wanted to reiterate it again. X naught is the real part, y naught is called the imaginary part, but even though it's called the imaginary part, it's still a real number. What makes it an imaginary number is the multiplicative I in front of it. So, x and y separately, they're real numbers, but because you multiply I to y naught, y, you get an imaginary number. And thus, I really want to repeat this again and again, so all you students will learn this and know about these things, is the fact that these complex numbers are made up of a real number, and the total of the I times the real number would make it an imaginary number. So a real number and an imaginary number would make a complex number. So here, as we see, when we take the limit z tends to z naught, we have the individual real and imaginary parts going to their limits as well, where x tends to x naught and y tends to y naught. And also, when you take a limit, as we've seen before, where you take z goes to z naught, the function to take z as an input, we get w naught. And here, w naught is basically equals to u naught plus I v naught. And individually, if you take the limit, if you break it down, say you apply the limit to f of z, you're individually applying the limit to u and v, as in you have, say for example, you've taken a limit, say for example, your function f of z is equals to, as you know, u plus I v. Now if you take the limit where z tends to z naught, you have here u, where you get it as a function of x naught, y naught, as in you've taken it to the limit, since when you take z to the limit z naught, you get x naught plus I y naught, or I can even write it in that fashion. Here, x comma y are being taken to the limit x naught comma y naught. Therefore, your u becomes a function of u, the number becomes a function of x naught y naught, and your imaginary part I v becomes a function of x naught y naught as well. So as you can see, what we can derive from this is taking the limit of the normal real part x naught comma y naught, where your limit is taken from x comma y to x naught y naught, you get this is taking the limit for u, which is a function of x and y. After that, it will be function of x naught, y naught. As in, it'll be a number that depends on x naught and y naught. Now, let's delve into theorem number 2. In further calculations, you'll probably have to use these theorems. Which is why I'm introducing all these theorems without the proofs, because it's important to learn how to use them. And for the case of the students who are predominantly taking this course, which are engineering students. So let's state theorem number 2. Let the limit where z tends to z naught, f of z will give us w naught, as we've seen before. We have the following additive property, in a sense that, say, we stated f of z as a function. Now we define another function, which is called which we denote with the capital F, which takes similar input z. As in, these two functional mapping are two different mappings, but they have the same input. See here, z and z. Let's say you were to take the limit of these two functions being added together. The limit then has the property that it will hit them. Basically, this is the same as writing as if this sort of limit operator is hitting them individually and then adding them. It's basically a similar statement. Limit z tends to z naught. Sorry, I can just instantly write it in the w way, since if you take the limit z tends to z naught to the small f of z, you get small w naught, and if you take the limit of the capital F of z, you get a different number, capital W naught. As I said before, taking the limit of two of them added together but in brackets is the same as taking the limit of them individually. Let's show another aspect of theorem, as in taking the limit of z tends to z naught of two functions multiplied with each other. Here f is a function as we've described before, and capital F is a different function taking the same input. Z is the same as multiplying w naught, small w naught, times capital W naught, in similar fashion like how we did with addition. And also, we shall see, you divide these functions together, they hold the same properties. Also, and you have the limit z tends to z naught, where small f z is being divided by capital F z, is equals to, if you take the limit of small f of z individually, you get small w naught, and taking the limit of capital F individually, you would get w naught. Basically, this theorem states that both of these are equivalent to each other, as did the other four things that we have shown before. Oh, and this is valid given that w naught is not equals to, capital W naught is not equals to 0 for obvious reasons. Thank you, and hope to see you in the next video.